Using the high-speed counter instructions. Not all processors support high-speed counters, and it is not just a matter of a firmware upgrade. If the processor does not have inputs pre-dedicated for use with an internal high-speed counter electronic circuit, the processor will not allow use of the high-speed counter instructions. The high-speed counter is an actual electronic circuit permanently connected to specific input terminals. When you initiate the high-speed counter instructions, it configures this high-speed counting circuit that is totally independent of the processor's program scan. The high-speed counter instruction can only instruct the counter data type addressed as C5:0 and none other. Once associated, that is C50, once associated with a high-speed counter instruction, C50 cannot be used by any other instructions in the program. This instruction actually configures hardware. With the count up and count down instructions in typical conventional use, they cannot increment the accumulate of a counter data type at a rate faster than the scan rate of the program. PLCs are synchronous. They gather the input data into the input image in the data table, then they execute the logic, they update the outputs, do a little housekeeping, and then update the input image again. If an input terminal changes state several times while the logic is being scanned and executed, in other words, from on to off and then from off back to on, the processor finds the same state at that input when it goes out and looks again that it found on the previous scan. Hence, there's no transition for the rung containing the count up or count down instruction, and the count is lost. So the high-speed counter is an actual electronic device permanently connected to specific input terminals. And when activated, it counts totally independent of the processor scan time. With the high-speed counter, the electronic circuit counts transitions as fast as the rise and fall time of the solid-state circuit will allow. In other words, it's a physical limitation based on internal capacitance and inductance. For the MicroLogix500, with the filter set as low as possible, set to 0.075 milliseconds, 75 microseconds, this is approximately 6600 Hertz at 50% duty cycle. So the electronic circuit, the high-speed counter electronic circuit, will count up to that frequency, 6600 Hertz. Bear in mind that as you reduce the interval of the filter on an input, you become more susceptible to noise and contact bounce. Now, the high-speed counter instruction offers you a variety of modes of operation. There's the up counter operation, uses a single-ended input. There's up with reset and hold. There's pulse and direction with external reset and hold. Then there's up and down with external reset and hold, encoder, and encoder with external reset and hold. That's 8 different modes of operation for the high-speed counter instruction. The instruction is your only interface to this high-speed counter from within the program. Specific input terminals are assigned for specific purposes, and they are inputs 0, 1, 2, and 3. So for different modes of operation, for instance, if you're going to do encoder, then input 0 is channel A, input 1 is channel B, and then inputs 2 and 3 are not used. If you're going to go encoder with external reset and hold, then input 0 is channel A, input 1 is channel B, input 2 is channel Z, and input 3 is the hold input. So those 4 inputs, input 0, 1, 2, and 3, are permanently electrically connected to the high-speed counter. You can't just pick and choose which of the 4 inputs you want to use for what function. So you definitely have to refer to the manual for specifics. The first mode that we demonstrated was the up mode. This is just a very basic application that has a accumulate value that increments up. When it matches the preset, the done bit comes on, just like a regular counter. However, we added a little piece of logic to reset the counter, because remember, a counter is not like a timer. Most timer instructions, the TON and TOF, on delay and off delay timers, when the run goes false, they reset. Not so with counter instruction types. So we have a little piece of code, rung 1, and it says reset high speed counter toggle. We're using an internal bit, B31:0, B310, and we're using the toggle function in RSLogix500. So if you right click on B31/0 and select toggle, it will change the existing state of that bit. Now, ordinarily you would right click on the done bit and toggle it off, but in this case we just want to reset C50. So to make it a one-click operation, when you right click on B31 in rung 1, it will change it to the on state, which will execute a reset for C50, and then it will unlatch B310, the bit you just toggled on. It makes it a one-step process. A nice little piece of code to remember when you need it. Also notice, and this takes people by surprise initially, that input 0 does not appear in the logic, because remember, inputs 0, 1, 2, and 3 are permanently hardwired to the high-speed counter. In the up mode of operation, only input 0 is used, and that is the up increment. Every time input 0 goes from false to true or from 0 to 1, off to on, it increments C50 by 1, even if it's at a speed much higher than the scan rate of the PLC, because remember, it's a direct connection. It's an electronic counter. The high-speed counter is our interface. The high-speed counter instruction is our interface between this high-speed electronic counter that's permanently connected to input 0, 1, 2, and 3. It is the permanent interface between that electronic high-speed counter and our program. So before we had you download the program, we had you increase the filter response or decrease the delay, however you would like to say it. We dropped it down to 0.07 milliseconds. Save, download, go online. And there's some notes in here that don't appear in all the labs, but they're reminders. The first one was in step 1. It says create a new project, add the following logic. Remember that the default baud rate for a DF1 driver is 9600. You don't want to use 9600. You want 19.2. It's faster. But you need to bump up the baud rate for the DF1 driver to 19.2 before you download. Otherwise, if you had a program already in the processor at 19.2, it's going to tell you the communication rates don't match. And if you make the wrong choice at that point, you lose communications, and then you have to go through a song and a dance, reconfigure the driver, get back in, bump up the baud rate, lose communications, go back, reconfigure the driver. It's better just always bump it up to 19.2 before you download. Okay, so if you lost communications, you have to open up RSLinks and re-auto configure the driver. But let's say you're golden. Toggle 0 SW or switch 0, input 0 until the accumulate register reaches 5. Well, you probably didn't see it. But does it actually reach 5? Yes, it does. How do you know that it reached 5? The done bit is set to 1. So the high-speed counter went through that pretty fast. Continue to increment input 0. What does the done bit do when the accumulate resets? It remains set to 1. You have to actually go reset the counter. Next, we had you change the preset to 20. We did this to demonstrate what you might consider a peculiarity of the high-speed counter and how it behaves. While watching the accumulate register actuate input 0, at some point, but no guarantee, you should see more than one increment for one flip of the switch. We dropped the filter down to 0.07 to increase the possibility of the high-speed counter picking up switch bounce. In other words, when the contacts go closed, they actually bounce. They make contact, open up again, and then close again. So with the filter set to as high a response as possible, you're more likely to get switch bounce. You may or may not. Anyway, so we had you slowly actuate input 0, and then we ask you this question. What happened when you reached the old preset? Remember, you entered a new preset of 20. The old preset was 5. The done bit is set to 1 as if the preset was not even increased. This is a peculiarity in that you have to execute a specific chunk of code after you have changed the preset if you want the high-speed counter to react to a new preset the next time that it is incremented. So just keep that in mind. If you change the preset in the program, while the program's running, there are other steps that you need to take to make the done bit come on when it reaches the new preset. The reason you might change presets on the fly is this. If you're doing some positioning and you have an encoder and you're using the high-speed counter instruction in an encoder mode and you change the preset to a number of counts that represents a distance, then you execute that distance, the done bit comes on, it stops, and then you put in a new preset because you want to go an additional distance incrementally. It would go the same distance it went before the done bit came on. Just something to keep in mind. If you like, when you're using the up mode type high-speed counter instruction, which is not the up with hold and reset, using a straight up mode, you can create your own hold and reset by putting permissives in the high-speed counter instruction rung and putting a permissive in the reset rung 1. So this is the code that you would write if you had an up mode type high-speed counter instruction, but you wanted hold and reset. To change the mode of operation of the high-speed counter instruction, it was simply a matter of dropping down the list and picking whatever mode of operation you wanted. In the next lab, we had you execute an up reset hold mode or type high-speed counter instruction. And from the manual there, you can see that input 0 is the up counter, input 1 is not used, input 2 is reset, input 3 is hold. So we had you reduce the preset. Remember, the preset was 20. We had you reduce it to 5, increment the up input 0, until the done bit comes on. Recognize the behavior, set the preset back to 20, cycle through until it responds to 20, then set the preset to 5, followed by toggling B310 and then increment with input 0. The moral to this little chunk of code or little bit of lab was, if you're going to change the preset and execute a reset instruction against C50 in the same scan. Notice that it says reset instruction, not toggle the reset input 2, but a reset instruction. Increment the counter to 2, then turn switch 3, input 3, the hold input on, and then toggle input 0 on and off several times. Did the count increment? No. Input 0 is hardwired into the high-speed counter as the up input. Input 3 is hardwired as a hold function. In other words, you can change a state from 0 to 1 on the hold input and have it ignore transitions on input 0. Turn input 3 off and increment the counter once. Then turn switch 2, input 2, reset on and off once. What did the accumulate value do? Zeroed out. The done bit, it remained on. Is it necessary to clear the done bit to use the counter? No. But if you wanted to clear the done bit, how would you do it? Execute a reset instruction addressed to memory location C5:0. Now, up in step 6, it said turn input 2 on and off once. That's the reset input. That resets the count. That's not the same as a reset instruction, which executes against the the counter data type C50. When you execute a reset with input 2, that is an electronic reset of the high-speed counter, not a reset of the data type C5:0. Another mode of operation, pulse and direction. We had you save, download, go online with all switches on the demo in the off position. Look closely at the high-speed counter instruction. Other than the type, what looks different? Both the count up and count down bits are shown as on. Remember that inputs 0 and 1 are configured directly to the electronic high-speed counter and are not shown in the logic. And input 0 is the count or the pulse, and input 1 is the direction. It's no longer called up, but it's called pulse and direction. While observing the accumulate register value, toggle input 0 on and off several repetitions. Did the accumulate increment as you expected? Yes. Place input 1 in the on position, and again, while observing the accumulate register, toggle the input 0 on and off several repetitions. What happened? Decremented the accumulate register or down counted. So when we were using up mode, input 0, every time it transitioned, we'll say from off to on, the counter incremented by 1. With pulse and direction, input 0 is no longer an up count, it's just a input for a pulse, and then input 1 determines whether it increments or decrements, up counts or down counts. Okay, step 5, toggle input 0 off, on and off until the accumulate is a negative number. Place input 1 in the off position, you've changed direction, and again, while observing the accumulate register, toggle input 0 on and off until the accumulate is greater than the preset. Does the done bit set when this occurs? No. Did the counter reset to 0 when the accumulate equaled the preset? No. Okay, modify your logic by adding a permissive in the rung of the high-speed instruction. Repeat the exercise of the counter with the bit enabled and with it disabled. Does this bit effectively act as a hold function? Yes. If you had a pulse generator driven by a wheel, say, riding on the belt of a reversing conveyor, and you wanted to know the position of an object on the conveyor, you also have a photo eye at the entrance and exit of the conveyor, how would you use the high-speed counter in the pulse direction mode? Simple. Anytime the conveyor is moving, you either energize the forward motor starter or the reverse motor starter. So you know when it's going forward or reverse, you simply reverse the direction on the high-speed counter. So once the object passes the photo eye at the entrance of the conveyor, then since you know the pulse rate of the wheel that's riding on the conveyor, and every pulse represents so many inches or so many feet, you can actually determine, once it breaks the beam on the photo eye, how far it is on the conveyor within the units of the length of distance for one pulse. If you reverse the conveyor, you simply reverse the direction on input 1 of the high-speed counter instruction, and you decrement the distance. The next mode was pulse direction with reset and hold. You simply drop down the type list and select pulse direction, reset, hold. Exercise the accumulate register up and down. You do this by switching the direction with input 1, and you increment or decrement with input 0. Use input 2 as a hold function and input 3 as a reset function. If the pulse direction, reset, hold, behaves identical to the pulse direction using logic to hold and reset, why have this mode of operation for the high-speed counter instruction? If the hold were tied to a non-high-speed input, the function would be limited to the scan time, meaning that if you wire a reset and hold directly to inputs 2 and 3, and you select a mode of operation that uses them directly, then they are not dependent on the scan time of the processor. If you're using logic, such as shown here in step 1, we see hold, we see input 3. If you use it directly, then it's going to be dependent upon the scan time of the processor, because it's not going to hold the counter until it goes through, scans the program, and basically puts the high-speed counter in the hold mode. Okay, now we go to the high-speed counter as up-down. We had you edit the logic, select up-down with all switches in the off position, toggle input 0 up, on and off several times while observing the accumulate register, then toggle input 1, which is a down count, on and off several repetitions while observing the accumulate register. Repeat the sequence with input 3 as a hold in the on position. Try toggling input 2 reset, on and off. Now, let me just point out that in this lab, you are using logic for hold and reset, not the hold and reset that's built into the electronic counter. Okay, very straightforward operation. Counts up and down with high-speed inputs to input 0 and input 1. Input 2 resets the accumulate in logic, and input 3 holds the accumulate. Now we're actually using the up-down with reset hold. So we're going to use, remember that it's the same inputs that we use for reset and hold, but now we're using them as a function of the high-speed counter, not in the logic. So it's going to respond faster. The reset and the hold is instantaneous instead of waiting for the next program scan. With all switches in the off position, toggle input 0 or the up input on and off several times while observing the accumulate register value. Then toggle input 1, which is the down count, on and off several repetitions while observing the accumulate register value. Repeat the sequence with input 3, the hold in the on position, and then try input 2, the reset, on and off. If both the up, down, and up, down, reset, hold function behave the same, why have the reset hold connected directly to the electronic high-speed counter? We already answered that. If you need a high-speed counter, then you probably need immediate response to a hold or immediate response to a reset, which you would not get if you used other inputs and logic to hold and reset the high-speed counter. Encoder mode with reset and hold. For the lack of a quadrature encoder, you will need to use the switches wired to input 0 and input 1. Input 0 will be channel A, input 1 is channel B, and when you get there, input 2 as channel Z. If your demo has an encoder, then by all means use it. So what we're going to look at here is how the high-speed counter recognizes direction from the encoder. So channel A goes high, then channel B goes high, then channel A goes low, channel B goes low. So A high, B high. If we reverse the direction of rotation of the shaft on the encoder, we get just the opposite sequence. B goes high, then A goes high, then B goes low, and A goes low. So if you compare the two, A goes high when B is low. If you look at the reverse direction, A goes high when B is already high. That's how the electronics recognizes direction. Okay, to simulate this, we're going to use channel A and B toggle switches. So using the forward switch sequence shown, simulate the encoder rotating in the forward direction for several counts. Then simulate the encoder rotating in the opposite direction. So if we look at the first set of sequences there, we have two switches, A and B. So we'll start out with them, we'll say both off. We turn on A, B is off. A is already on, so we turn on B. Then we turn off A, then we turn off B. That's the forward sequence. Compared below to the reverse switch sequence, B goes on first instead of A. If you look right above the reverse sequence, you'll see the difference. So the forward sequence, A goes on, and then B goes on. With reverse, B goes on, then A. Toggling input 2 on and off at any time will simulate a marker pulse event, resetting the count back to 0. If you do not have to use the marker pulse, you don't have to use the marker pulse if you want to continuously accumulate counts. Keeping in mind that the limits of the count is minus 32,768 to a positive 32,767. Try using input 3 to hold or inhibit incrementing and decrementing the count. Once again, the forward switch sequence for one cycle will begin with A, the leading edge of A, occurring when channel B is off. The reverse sequence cycle, channel B leading edge occurs when channel A is off. Well, the high-speed count instruction, this is really nice for not losing counts if you have high-speed inputs, or if you have a device that's transitioning at a rate faster than the scan rate of the processor. But let's say that you want to actually control something and not want to wait for the scan of the processor to update the output image and turn the outputs on or off. In walks the high-speed load instruction. Very simple instruction to use. You need to look it over closely and try it out before you actually apply it in an application. C50 is the only high-speed counter for a MicroLogix 1000, and the length is always 5 for the high-speed load instruction. So the counter is C5:0, the length is always 5. All you have to pick are 5 consecutive 16-bit words that you want to use for your source, which would be an N7 data file of 5 words or a B3 data file of 5 words. In this case, we're going to use N7 0, 1, 2, 3, and 4. The goal here with the load instruction is for the high-speed counter to control outputs without interfering with outputs controlled from the logic. The high-speed counter can directly control any of the lower byte of word 0 in the output data file. Now we've only got 4 outputs in this MicroLogix 1000, but the larger MicroLogix 1000s have more than 4 outputs. So you can control the lower byte, which is the lower 8 bits, directly with the high-speed counter based on a high preset or a low preset. The mask is a method of pinpointing which outputs will respond to the data. So really, the output mask is what prevents the high-speed counter from directly interfering with outputs that are controlled from the logic. So use the mask to block any of the source from the destination word for individual bits that are controlled directly by the logic. The high-speed load is capable of loading a high preset as well as a low preset into the high-speed counter and 2 separate bit patterns for the lower byte of output word. In this case, output :0.0/0 through 7. When the accumulate is equal to the high preset, the high output source N7.1 is passed through the mask to word 0 in the output data file. Now the HSL doesn't show a destination. The destination's predetermined and fixed. It is the first 8 bits or the lower byte of the output word 0. In this instance, shown here, the accum equals the preset and the source is sent to the destination through the mask. But since the mask is all zeros and zeros block the source from reaching the destination, none of the outputs are changed. Encoder mode with reset and hold. For the lack of a quadrature encoder, you will need to use the switches wired to input 0 and input 1. Input 0 will be channel A, input 1 is channel B, and when you get there, input 2 as channel Z. If your demo has an encoder, then by all means use it. So what we're going to look at here is how the high-speed counter recognizes direction from the encoder. So channel A goes high, then channel B goes high, then channel A goes low, channel B goes low. So A high, B high. If we reverse the direction of rotation of the shaft on the encoder, we get just the opposite sequence. B goes high, then A goes high, then B goes low, and A goes low. So if you compare the two, A goes high when B is low. If you look at the reverse direction, A goes high when B is already high. That's how the electronics recognizes direction. Okay, to simulate this, we're going to use channel A and B toggle switches. So using the forward switch sequence shown, simulate the encoder rotating in the forward direction for several counts. Then simulate the encoder rotating in the opposite direction. So if we look at the first set of sequences there, we have two switches, A and B. So we'll start out with them, we'll say both off. We turn on A, B is off. A is already on, so we turn on B. Then we turn off A, then we turn off B. That's the forward sequence. Compared below to the reverse switch sequence, B goes on first instead of A. If you look right above the reverse sequence, you'll see the difference. So the forward sequence, A goes on, and then B goes on. With reverse, B goes on, then A. Toggling input 2 on and off at any time will simulate a marker pulse event, resetting the count back to 0. If you do not have to use the marker pulse, you don't have to use the marker pulse if you want to continuously accumulate counts. Keeping in mind that the limits of the count is minus 32,768 to a positive 32,767. Try using input 3 to hold or inhibit incrementing and decrementing the count. Once again, the forward switch sequence for one cycle will begin with A, the leading edge of A, occurring when channel B is off. The reverse sequence cycle, channel B leading edge occurs when channel A is off. Well, the high-speed count instruction, this is really nice for not losing counts if you have high-speed inputs, or if you have a device that's transitioning at a rate faster than the scan rate of the processor. But let's say that you want to actually control something and not want to wait for the scan of the processor to update the output image and turn the outputs on or off. In walks the high-speed load instruction. Very simple instruction to use. You need to look it over closely and try it out before you actually apply it in an application. C50 is the only high-speed counter for a MicroLogix 1000, and the length is always 5 for the high-speed load instruction. So the counter is C5:0, the length is always 5. All you have to pick are 5 consecutive 16-bit words that you want to use for your source, which would be an N7 data file of 5 words or a B3 data file of 5 words. In this case, we're going to use N7 0, 1, 2, 3, and 4. The goal here with the load instruction is for the high-speed counter to control outputs without interfering with outputs controlled from the logic. The high-speed counter can directly control any of the lower byte of word 0 in the output data file. Now we've only got 4 outputs in this MicroLogix 1000, but the larger MicroLogix 1000s have more than 4 outputs. So you can control the lower byte, which is the lower 8 bits, directly with the high-speed counter based on a high preset or a low preset. The mask is a method of pinpointing which outputs will respond to the data. So really, the output mask is what prevents the high-speed counter from directly interfering with outputs that are controlled from the logic. So use the mask to block any of the source from the destination word for individual bits that are controlled directly by the logic. The high-speed load is capable of loading a high preset as well as a low preset into the high-speed counter and 2 separate bit patterns for the lower byte of output word. In this case, output colon 0.0 slash 0 through 7. When the accumulate is equal to the high preset, the high output source N71 is passed through the mask to word 0 in the output data file. Now the HSL doesn't show a destination. The destination's predetermined and fixed. It is the first 8 bits or the lower byte of the output word 0. In this instance, shown here, the accum equals the preset and the source is sent to the destination through the mask. But since the mask is all zeros and zeros block the source from reaching the destination, none of the outputs are changed. In this instance, when the accumulate equals the high preset and the source is sent to the destination through the mask has 2 bits that are 1s. These values are passed on to outputs 1 and 2. Compare this next example with the previous. In the previous example, the destination bits were all off. In this example, bits 0, 1, 2, and 3 are on, and the mask of all zeros blocks the high-speed counter from changing the state to 0. If the mask blocks the source, the destinations stay the same. Remember that you can't affect the outputs by ignoring them. You either tell them 0 or 1, or in this case, nothing. The mask blocks any change. However, with the same mask value as in the previous example, the door is open to update bits 1 and 2 from the source. So remember, you have a high and a low preset, and you have a separate bit pattern to control the first 8 bits of the lower byte, unique to the high preset and the low preset. A bit value of 0 blocks the source from updating the destination, and a value of 1 passes on the state, whether on or off, of the source. The high-speed load instruction loads 1 mask, 2 presets, and a unique source bit pattern to update the outputs with through the mask for each of the 2 presets. So it loads a mask, 2 presets, and 2 unique source bit patterns to update the outputs with. The mask prevents the high-speed counter from updating output bits that you may be controlling directly from the logic. In the case where you have applied logic against the same outputs being controlled by the high-speed counter, the first rule of PLCs applies. Last man wins. The last execution before the I/O update determines the actual state of the output. If the high-speed counter updates first and then the logic updates the same bits in the output data file word 0, the logic had the last and final say as to the state of that output. I don't think you would do that on purpose to write code that controls an output and try to control it directly from a high-speed counter. But nonetheless, if it happens, this is the rule. Let's do this one more time. The high-speed counter load instruction addresses the high-speed counter. In the MicroLogix1000, you only have one high-speed counter, C5:0. It loads 5 16-bit words from the source. In this case, we used N7:0. It loads a mask, a output high source, high preset, output low source, and low preset. The output high source and high preset are a pair. Output low source and low preset are a pair. If the high preset is matched by the accumulate, then the output high source bit pattern is transferred to the lower byte of word 0 of the output file. Whether or not that high output the high source bit pattern reaches the actual outputs is determined by the bit pattern of the mask. So there's only one mask bit pattern, and it's used for both when the accumulate reaches the high preset or when the accumulate reaches the low preset. But it does give you a different bit pattern that you can effect changes in the output state based on reaching the high source or the low source, or rather the high preset and the low preset. A bit value of 0 blocks the source from updating the destination in the mask, and a value of 1 passes on the state. The mask prevents the high-speed counter from updating output bits that you may be controlling directly from program logic. In the case where you have applied logic against the same outputs being controlled by the high-speed counter, the first rule of PLCs applies. Last man wins. The last execution before the I/O update determines the actual state of the output. And since these occur independent of each other, I can see some applications where you would control the output from the logic but override it with a high-speed counter. If the high-speed counter updates first and then the logic updates the same bits in the output data file, word 0, the logic had the last and final say as to the state of that output. Explanation of the high-speed counter reset accumulator instruction takes a little bit of explanation. Remember that the high-speed counter is actually an electronic counter that has nothing to do with the program in the PLC. It is a separate electronic counter permanently wired to inputs 0, input 1, input 2, and input 3. And we've went through quite a few of the different modes of operation so far. So think about this. The electronic counter can increment based on the rise and fall rate of the electronics itself, which we mentioned was 6600 Hertz, meaning it's a physical limitation. It is not limited by the scan rate, meaning that a count up or count down instruction that is instructing C50, C51, C52, any of the counter predefined data types, they can only increment or decrement the data file after each input image scan. So whatever the input image was doing, actually the input image is really the input word in the processor's memory, not the literal on and off state of the inputs or the output image, the on and off state of the outputs. So the high-speed counter accumulate register, when actually having been applied as a high-speed counter, that accumulate is not going to be equal to the accumulate register in C50 at all times. So the C50's accumulate register will update from the register that's actually in the high-speed counter, the electronic. So if you want to reset the high-speed counter, are you wanting to reset the accumulate value in the electronic counter or the accumulate value that's actually an image that was updated by the instruction in the logic? The HSC reset accumulator instruction, RAC instruction, is for the purpose of specifically loading, specifically loading a value into the accumulator of both the high-speed counter's image, the high-speed counter's accumulate, and the image accumulate. So in our logic here, we have a first pass bit. You could also do the same thing by toggling B30/0 that resets both accumulate registers, moves new values, we'll call them startup values, into specific locations, in the 5-word file that we're going to use in the high-speed counter load instruction that we just went over, as you can see in rung 0. In rung 1, as soon as the first pass bit has gone back low, then rung 1 will be true. So rung 0 will be true for the first scan, but not rung 1. Second scan, rung 0 will be false, and rung 1 will be true, and it will configure the high-speed counter as an encoder high-speed counter. And then rung 2 is part of the normal process. When the first scan has finished, the second scan will find this rung true, and the high-speed counter instruction will configure the high-speed counter. When the high-speed counter has incremented to the first high preset, the bit pattern from the high output source is passed through the mask to the lower byte of the data file output word 0, and the appropriate changes should be seen at the output LEDs. The logic separately reads the accumulate equals 2 and moves new values into the integer file for the subsequent high-speed counter load. So you can continually change the high and low presets and bit patterns on the fly using this logic. Now, if your logic faults when you downloaded and went online, you probably forgot to put a value in the preset for the high-speed counter. The most common mistake in all the labs, in all the books, is using a true-if-on instead of a true-if-off. People don't know the little slash. Notice the slash across the symbol for relay contacts. The most common mistake in this particular lab is not setting the high-speed counter to encoder type and not putting a preset in. When the high-speed counter has incremented to the new high preset, the bit pattern from the high output source is passed through the mask to the lower byte of the data file output word 0, and the appropriate changes should be seen on the output LEDs. The logic separately reads accum equals 5 and moves new values into the integer file for the subsequent high-speed counter load. Okay. So we open and lock on top data files 0, 5, and 7 as shown. Toggle inputs 0 and 1 in the forward sequence used in the previous lab while keeping a close eye on the accumulate register and the output LEDs on the demo on the hardware trainer, or the output bits in the data table. Sequence the inputs on your hardware trainer until the high-speed counter is reset. In case you are wondering why you did not do this with a count up instruction, which could have kept up with the speed that you've been flipping these switches, because we're demonstrating an application where if this were an encoder, a count up instruction would have missed at least half or more of the counts. We've looked at the case of directly controlling outputs on the lower byte of output word 0 by means of the high-speed load, the mask, the high output source, low output source, high preset, and low preset. However, that directly controls outputs. What if you wanted to execute some specific logic at the event of the high or low preset equaling the accumulate register? Then you must use the high-speed counter interrupt. To use the high-speed counter interrupt, you need to do two things. First of all, the logic that you want executed has to be placed in program file number 4 and no place else. And you need to enable the high-speed interrupt, HSC. This rung can be unconditional, as shown below, or you can add permissives in the rung to condition under what circumstances that the interrupt is enabled. If the HSC is executed when an interrupt is pending, it will be executed immediately. So this takes the high-speed counter one step further in that with the high-speed load you can load up and control specific outputs when the count reaches a high preset or a low preset. This takes it one step further in that when it reaches a preset, it can actually interrupt and execute some specific logic immediately. There are two instructions that we haven't talked about yet, and these fall into the same category with interrupts and with high-speed counters, looking to have an effect on outputs or to read inputs more immediately. And these are the immediate input with mask and immediate output with mask. These two instructions have values for the mask that eliminate the need of a mask. All F's hexadecimal is hexadecimal for binary all ones, or 16 ones, meaning that all 16 inputs or outputs will immediately be updated. So these instructions come with a mask. The mask in the following immediate input update will allow only input 1 and input 0 to be updated in the input image table. The mask in the immediate output with mask instruction will allow only output 0, 1, and 2 to be updated. Very simple instructions. You can put them as many places as you want in your program. Basically, when the program gets to rung 2, it immediately updates input word 0. It goes out, reads the actual electrical state at those terminals, transfers it into memory. The immediate output stops execution of the program and immediately takes the output image stored in memory, which is designated by word 0:0.0, moves it out to the actual output terminals and changes the state. Very straightforward instructions. The immediate input with mask and immediate output with mask always behave the exact same way. If it's an immediate input, it goes out and reads whatever word you've designated in the slot parameter, reads it in through the mask into that word in memory. The immediate output takes the address from memory and sends it out to the actual outputs through the mask. Here we got some more examples where we have a mask of 4 hexadecimal, which means that the third bit is turned on, which means only input 2 will be read in and updated in the input image and will have an effect on the program scan, or the results of the program scan. In the second example, for an output image, immediate output with mask, we have 5 hex, which is the first bit and the third bit are 1, which means output 0 and 2 are the only ones that are immediately updated. So the immediate input and output with mask instructions are very straightforward and simple. You only need to remember to use the appropriate mask if you don't want to read in all of the inputs and update all of the outputs every time you execute these instructions. As I said before, permissives can be placed in the rungs to control the conditions under which the immediate updates take place. They can also be placed at the beginning of, at the end of, subroutines that are conditionally executed.